In the depths of space, suspended in the eternal night that surrounds our small blue world, there exists a point of light so close that it mocks the very idea of cosmic distance, a stellar system that has haunted human imagination for generations, not because of what it promises, but because of how near it stands to us in the incomprehensible vastness of the galaxy. Alpha Centauri. The name itself carries weight, a designation that has appeared in science fiction novels and speculative essays, in the dreams of engineers sketching starship designs and children staring up at southern skies, wondering what worlds might circle those distant suns. For more than a century, since we first understood what stars truly were, Alpha Centauri has represented something more than astronomical curiosity. It has been our nearest neighbor in a neighborhood measured in light years, our most accessible target in a universe designed to keep its secrets separate by gulfs of space so profound that even light, moving at its ultimate cosmic speed limit, takes years to cross the distances between one stellar system and another. 4.37 light-years. That is the distance that separates our Sun from the triple star system we call Alpha Centauri, a measurement that seems almost trivial when written in the specialized notation of astronomical catalogs, yet represents a void so absolute that no human technology has ever crossed even a meaningful fraction of it. To grasp this distance requires more than mathematics. Consider that light, which traverses the space between Earth and Moon in just over a second, which covers the distance from our planet to our star in 8 minutes, requires more than 4 years to reach Alpha Centauri. Every photon that arrives in our telescopes from those stars began its journey when our present moment was still future, when the very arrangement of human affairs was different, when children not yet born would be the ones to finally detect that ancient light. And yet, in galactic terms, this distance is nothing. The Milky Way stretches across 100,000 light-years of space. Alpha Centauri lies so close to us that if our galaxy were reduced to the size of North America, the distance between our Sun and Alpha Centauri would be less than the width of a pencil line. This proximity has mattered to us. It has mattered in ways both practical and philosophical, shaping how we think about our place in the cosmos and our future among the stars. When scientists first began seriously contemplating interstellar travel, when engineers moved beyond the realm of pure fantasy to consider what technologies might actually propel a vessel across the light years, Alpha Centauri was always the destination they calculated for, the target they used to test their equations and constrain their designs. Project Daedalus in the 1970s, Breakthrough Starshot in the 21st century, countless other proposals spanning decades of human ingenuity, all oriented themselves toward those nearby stars. The reasoning was straightforward. If humanity were to ever send an emissary to another stellar system, if we were to ever expand beyond this single solar system that has contained all of human history, Alpha Centauri represented the smallest possible step, the shortest journey into the interstellar void. And embedded within this practical consideration was a deeper hope, an assumption that guided research and shaped speculation for generations. If planets orbited those nearby stars, if worlds existed in the habitable zones where liquid water could persist on solid surfaces, then perhaps life had emerged there too, perhaps intelligence. Perhaps civilizations were developing technologies and asking their own questions about the cosmos, looking back toward our Sun with the same wonder we directed toward theirs. The discovery that Alpha Centauri was not a single star but a system of 3 only deepened this fascination. The 2 brightest components, Alpha Centauri A and Alpha Centauri B, orbit each other in a gravitational dance that takes just under 80 years to complete, 2 stars bound together in mutual orbit, circling a common center of mass. Alpha Centauri. A is slightly larger and brighter than our own Sun, a golden star classified as spectral type G2, remarkably similar to the star that warms Earth. Alpha Centauri b is somewhat smaller and cooler, an orange K-type star still luminous enough to illuminate worlds with light that would seem only slightly dimmer and redder than the light we know. Together, this binary pair forms one of the most prominent stellar systems visible from Earth's southern hemisphere, bright enough to be known to human cultures for thousands of years, significant enough to earn designation as the third brightest star system in the night sky. But the system holds a third component, a member discovered only in the 20th century, a star so faint that despite its relative proximity it remained hidden from human awareness until photographic surveys finally detected its dim red glow. Proxima Centauri. The name means nearest, and it is precisely that. A red dwarf star that happens to be positioned slightly closer to our solar system than the main binary pair, making it, at just over 4.2 light-years distant, the single nearest star to Earth beyond our own Sun. Proxima Centauri is a different kind of star entirely from its two brighter companions. Where Alpha Centauri A and B shine with steady light and possess the same basic structure as our Sun, Proxima is a red dwarf, a class of star that represents the most common stellar type in the galaxy, yet remained largely unstudied for decades precisely because red dwarfs are so faint. These stars are small, typically less than half the mass of our Sun, and they burn their hydrogen fuel so slowly that their lifespans stretch into trillions of years, far longer than the current age of the universe itself. They glow with dim red light, cool by stellar standards, their surface temperatures barely hot enough to sustain the nuclear fusion reactions that power all stars. For most of astronomical history, red dwarfs were footnotes, curiosities catalogued but not deeply investigated, assumed to be simple, stable, and largely uninteresting. Their faintness meant that even nearby examples were difficult to study in detail, and the assumption prevailed that these small cool stars would host small cool planetary systems, if they hosted planets at all, systems unlikely to interest anyone searching for habitable worlds or signs of life. This assumption began to erode in the early 21st century as new technologies and new telescopes made the detection of exoplanets increasingly routine. The first planets discovered around other stars were giants, massive worlds orbiting close to their parent stars, easy to detect because of their strong gravitational influence and the correspondingly large signals they produced in our instruments. But as techniques improved, as the precision of our measurements increased, astronomers began finding smaller worlds, Earth-sized planets and super-Earths, rocky bodies that might possess solid surfaces and atmospheres. And with surprising frequency, these rocky planets were discovered orbiting red dwarf stars. The reasons made sense in retrospect. Red dwarfs are small and dim, which means planets orbiting in their habitable zones, the regions where temperatures might allow liquid water, orbit very close to these stars, much closer than Earth orbits the Sun. These close orbits produce strong detectable signals, making such planets easier to find despite the faintness of their host stars. And because red dwarfs are so numerous, making up perhaps 70 to 80% of all stars in the galaxy, the sheer statistical weight of their numbers meant that a significant fraction of all rocky planets in the Milky Way likely orbit red dwarf stars. The habitable zone concept became central to how astronomers thought about the potential for life beyond Earth. This zone represents the range of orbital distances from a star where a rocky planet with an atmosphere could maintain liquid water on its surface, a condition considered essential for life as we understand it. For stars like our Sun, this zone lies roughly where Earth and Mars orbit, a region neither too hot nor too cold, balanced between the intense radiation closer to the star and the frozen darkness farther out. For red dwarfs, with their much lower luminosity, the habitable zone contracts dramatically, pulled in close to the star itself. A planet orbiting in the habitable zone of a red dwarf might circle its star at a distance less than 1/10 the distance between Earth and our Sun, completing an orbit in a matter of days or weeks rather than a full year. this proximity raised concerns about tidal locking and stellar activity, but it also meant that habitable zone planets around red dwarfs would be relatively easy to detect and study, accessible to our instruments in ways that more distant planets would not be. When astronomers announced in 2016 that they had discovered a planet orbiting Proxima Centauri, the news reverberated through both scientific communities and popular imagination. Here was a world, designated Proxima Centauri b, or simply Proxima b, orbiting the nearest star to our own, positioned squarely within that star's habitable zone. The planet was detected through the radial velocity method, measuring the slight wobble that Proxima Centauri experiences as the planet's gravity tugs on the star during its orbit. The data suggested a world with a minimum mass about 1.3 times that of Earth, potentially a rocky planet not dramatically larger than our own world, completing an orbit around Proxima every 11.2 days. Its orbital distance placed it at roughly 5% of the distance between Earth and the Sun, close by the standards of our solar system, but positioned at exactly the right distance to potentially maintain liquid water given the dim luminosity of its red dwarf host. The discovery seemed almost too perfect, too aligned with human hopes. The nearest star to Earth hosted a potentially habitable planet. The universe had placed, right on our doorstep, the exact kind of world we had been searching for. The announcement triggered an explosion of scientific modeling and speculation. Researchers began constructing computer simulations to explore what conditions might exist on Proxima b, what its atmosphere might contain, whether water might pool in oceans on its surface, whether the planet might be a true Earth analog or something stranger, a world shaped by the unique conditions of orbiting a red dwarf star. Early models were cautiously optimistic. Yes, the planet was likely tidally locked, with one face perpetually turned toward Proxima Centauri and the other facing eternal night, a consequence of the strong tidal forces exerted over billions of years of evolution in such a close orbit. But atmospheric models suggested that if the planet possessed a sufficiently thick atmosphere, heat could be redistributed from the day side to the night side, preventing the atmosphere from freezing out entirely on the dark hemisphere and creating a potentially habitable band between eternal day and eternal night. Some models explored the possibility of a water world, a planet completely covered by a global ocean that could circulate heat and maintain stability even under the extreme conditions of tidal locking. Others considered the magnetic field requirements, noting that a strong planetary magnetic field might shield the world from the stellar wind and radiation environment, protecting any atmosphere and surface water from erosion and degradation over geological time. The optimism was infectious. Here was a nearby world that might be studied in unprecedented detail. The proximity of Proxima b meant that future telescopes, instruments more advanced than anything currently operating, might be able to directly image the planet, to analyze its atmosphere through spectroscopy, to search for biosignatures, chemical indicators that might suggest the presence of life. Some scientists began discussing the planet as the prime target for humanity's first interstellar probe, the destination that Breakthrough Starshot's tiny light-sail spacecraft might reach within a few decades if the technology could be developed and deployed. News media picked up the story, translating the careful scientific language into headlines about Earth's nearest neighbor, a potentially habitable world just next door in cosmic terms, a place where life might have emerged and evolved under an alien sun. The dream of Alpha Centauri as a destination, as a system worth reaching, seemed suddenly validated by observation and data. But beneath this optimism, questions remained, concerns that grew more pressing as astronomers continued to observe Proxima Centauri and similar red dwarf stars with increasing precision. Red dwarfs had always been known to be variable stars, prone to flares and bursts of activity that could temporarily increase their brightness by significant factors. These flares were understood to be magnetic in origin, related to the complex magnetic fields that red dwarfs generate through their internal structure. Unlike Sun-like stars, which have a radiative core surrounded by a convective outer layer, red dwarfs are fully convective throughout their entire volume. The energy generated by fusion in their cores is transported to their surfaces entirely through churning convection, vast, overturning cells of plasma that create and sustain powerful magnetic fields. These fields become tangled and stressed, and when magnetic field lines reconnect, the energy released manifests as stellar flares, violent eruptions that blast radiation and charged particles into space. The concern was whether planets orbiting so close to these active stars could survive such bombardment, whether atmospheres could persist in the face of repeated flare impacts, whether the surface environment could remain stable enough for life to emerge and persist. Early observations of Proxima Centauri confirmed that the star was indeed active, prone to frequent flaring events. Some of these flares were modest, brief increases in brightness that added little to the star's overall energy output. But others were massive, superflares that increased Proxima's luminosity by factors of 10 or more, flooding the inner system with ultraviolet and X-ray radiation far more intense than anything experienced by planets in our solar system. The frequency of these events was concerning. While our Sun produces flares occasionally, usually associated with sunspot cycles and magnetic activity, Proxima Centauri seemed to flare with regularity, producing significant outbursts multiple times per year. For a planet orbiting so close to this star, each flare would represent a sudden, intense dose of high-energy radiation, the kind of exposure that could damage or strip away atmospheric molecules, break apart water vapor, and scour surfaces with ionizing radiation. The question became quantitative. How much radiation could an atmosphere withstand before being eroded away? How strong would a planetary magnetic field need to be to deflect the stellar wind and prevent atmospheric stripping? What geological processes might replenish atmospheric gases lost to space, and could those processes operate quickly enough to maintain equilibrium against continuous losses? These were questions that required detailed observations, precise measurements of the stellar environment, and sophisticated modeling of planetary atmospheres under extreme conditions. And they were questions that, for years, remained only partially answered, constrained by the limited capabilities of existing telescopes and the difficulty of observing faint red dwarf stars in the kind of detail necessary to characterize their radiation environments. The James Webb Space Telescope changed what was possible. Launched in late 2021 and brought into operation in 2022, JWST represented a generational leap in astronomical capability, an infrared observatory of unprecedented sensitivity and precision designed to study the earliest galaxies, the formation of stars and planetary systems, and the atmospheres of exoplanets. Its large mirror and advanced instrumentation allowed it to collect light across infrared wavelengths with a clarity and depth that no previous telescope could match. And while much of its early observation time was dedicated to distant galaxies and exotic phenomena far across the universe, a portion of its schedule was allocated to studying nearby stars and their planetary systems, including detailed observations of Proxima Centauri and the planets that orbit it. The data that returned from these observations did not validate the earlier optimism. Instead, they revealed an environment far more hostile than most models had predicted, a system where the violence of stellar activity so thoroughly dominated the space around Proxima Centauri that the survival of any atmosphere on Proxima b seemed not just unlikely, but essentially impossible over geological timescales. The measurements were precise and unambiguous. JWST's instruments characterized the stellar flare activity in exquisite detail, capturing not just the visible and near-infrared increases in brightness, but the full spectrum of radiation emitted during flare events, including the extreme ultraviolet and X-ray wavelengths that are most destructive to planetary atmospheres. The intensity of this high-energy radiation during major flare events exceeded worst-case predictions. A planet orbiting as close as Proxima b would be bathed in ultraviolet flux levels hundreds or thousands of times stronger than Earth experiences from our Sun, and this exposure would not be occasional but regular, occurring with nearly every significant flare event. Ultraviolet radiation interacts with atmospheric molecules in destructive ways. High-energy photons can break molecular bonds, dissociating water vapor into hydrogen and oxygen, splitting apart carbon dioxide, destroying complex molecules that might otherwise contribute to a stable climate. The lighter hydrogen atoms, once freed from molecular bonds, can escape to space, particularly from a low-gravity world like Proxima b, where escape velocities are lower than on Earth. Over time, this process, called photodissociation and atmospheric escape, strips away lighter elements and leaves atmospheres depleted, oxidized, and ultimately thinner. On Earth, our atmosphere is protected from this process by multiple factors. The distance from our Sun reduces the intensity of ultraviolet radiation we receive. Our planet's strong magnetic field deflects much of the solar wind, the stream of charged particles that flows outward from the Sun, preventing it from directly impacting and eroding our atmosphere. And our Sun is a relatively quiet star, producing flares infrequently and at energy levels that, while occasionally disruptive to satellites and power grids, do not fundamentally threaten the existence of our atmosphere. Proxima b has none of these protections. The close orbital distance means that the inverse square law works against any planetary atmosphere, intensifying the radiation received during quiet periods and multiplying the destructive power during flares. The stellar wind from Proxima Centauri, composed of charged particles accelerated away from the star's surface, flows past the planet at close range, and without a strong magnetic field to deflect this wind, it can interact directly with the upper atmosphere, stripping away ions and molecules over time, and the question of whether Proxima b possesses a strong magnetic field remains uncertain. Magnetic fields are generated by dynamo processes in a planet's core, requiring a liquid, electrically conductive region undergoing convective motion. Earth's magnetic field is sustained by convection in its molten iron outer core, a process enabled by the heat flowing from the solidification of the inner core and residual heat from the planet's formation. For Proxima b, the conditions necessary to sustain such a dynamo are unclear. Tidal heating from the planet's close orbit might help maintain a molten core, but the planet's relatively low mass and the possibility that tidal locking has reduced internal heat generation raise questions about whether a protective magnetic field could exist at all, or, if it exists, whether it would be strong enough to shield against the intense stellar wind and radiation environment. JWST's spectroscopic observations searched for signs of an atmosphere around Proxima b using transit methods, attempting to detect the absorption signatures that would indicate the presence of atmospheric gases as the planet passed in front of its star from our perspective. The results were negative. No clear atmospheric signatures were detected, no signs of water vapor, carbon dioxide, methane, or any of the other gases that might constitute a substantial atmosphere. The absence of a detection does not prove the absolute absence of an atmosphere. Thin atmospheres or clouds could obscure certain spectral features, and the observations are at the limits of current technology. But the failure to detect any atmospheric signatures when models had suggested that such signatures should be detectable if present was itself informative. It suggested that if Proxima b ever possessed a substantial atmosphere, it either never developed one in the first place or lost it long ago to the relentless assault of stellar activity. Further observations revealed the mechanism of destruction in even greater detail. During major flare events, JWST instruments detected massive eruptions of plasma from Proxima Centauri's surface, coronal mass ejections on a scale that dwarfed anything produced by our Sun. These plasma clouds, dense regions of magnetized charged particles, sweep outward from the star at high velocities, and when they impact a planet orbiting as close as Proxima b, the effects are catastrophic for any atmosphere. The magnetic fields embedded in the plasma interact with any planetary magnetic field, and in the absence of sufficient protection, the plasma can directly strike the upper atmosphere, compressing it, heating it, and accelerating atmospheric particles to escape velocities. A single major coronal mass ejection impact could strip away a significant fraction of an atmosphere's mass, and with such events occurring potentially dozens or hundreds of times over a planet's lifetime, the cumulative effect would be total atmospheric loss unless geological processes could replenish the atmosphere faster than it is being stripped away. The geology of Proxima b itself became a subject of scrutiny. On Earth, volcanic activity and other geological processes release gases into the atmosphere, a form of planetary outgassing that has sustained and modified Earth's atmosphere over billions of years. Could similar processes operate on Proxima b, continuously replenishing atmospheric gases lost to stellar activity and maintaining a stable atmosphere despite the hostile conditions? The answer depends on the planet's internal heat budget and its tectonic activity. Earth remains geologically active because it retains significant internal heat from its formation and from the radioactive decay of elements in its interior, and because plate tectonics provides a mechanism for heat to escape and materials to cycle between the surface and the interior. Whether Proxima b possesses similar geological vigor depends on factors that are difficult to constrain from observations alone: the planet's composition, the amount of radioactive elements in its interior, the presence or absence of tectonic activity, the rate of tidal heating from interactions with its star. All of these influence the rate at which volcanic gases might be released. But even generous assumptions about geological outgassing rates struggle to balance against the measured rates of atmospheric loss under the intense radiation and stellar wind environment that JWST observations revealed. The destruction exceeds any plausible replenishment. Water, the molecule so central to our conception of habitability, faces particular challenges on a world like Proxima b. Water vapor in an atmosphere exposed to intense ultraviolet radiation is photodissociated into hydrogen and oxygen. The hydrogen, being light, escapes to space. The oxygen, being heavier, remains but becomes available to oxidize surface minerals, effectively sequestering it into the planetary crust. Over time, this process represents a net loss of water from the planet. Even if Proxima b formed with substantial water, comparable to Earth's oceans or more, the continuous photodissociation and hydrogen escape over billions of years would gradually desiccate the world, baking away its water and leaving behind an oxidized, dry surface. The process is irreversible on geological timescales. Once hydrogen is lost to space, there is no mechanism to return it to the planet. The water is gone, transformed into surface oxides and lost hydrogen, a one-way process driven by stellar radiation that operates as long as the star continues to shine. The tidal locking of Proxima b adds additional layers of complexity and hostility to the environment. A tidally locked planet does not rotate relative to its star, meaning one hemisphere perpetually faces the star while the other faces away into space. On the day side, the star hangs motionless in the sky, fixed at a single position, pouring its radiation continuously onto the same hemisphere for billions of years. On the night side, the star never rises, and the only illumination comes from starlight and perhaps the faint glow of the dayside atmosphere if one exists. This configuration creates extreme temperature gradients. Without atmospheric circulation to redistribute heat, the day side could become scorching hot while the night side freezes. Early atmospheric models suggested that a sufficiently thick atmosphere could transport heat from the day side to the night side through atmospheric circulation, creating winds that would moderate the temperature extremes and potentially allow liquid water to exist in a band between the extremes. But these models assumed the presence of a thick atmosphere, precisely the thing that JWST observations suggest Proxima b lacks. Without that atmosphere, the temperature gradients become extreme, and any water present would either boil away on the day side or freeze solid on the night side, with no stable liquid phase region except perhaps briefly at the terminator, the boundary between day and night, and even there the conditions would be marginal at best. The surface of Proxima b, if we could observe it directly, likely presents a desolate vista, a world scoured by radiation, stripped of atmosphere, desiccated of water, and locked in a configuration that has concentrated stellar energy on one hemisphere while leaving the other in frozen darkness for aeons. The day side might be a radiation-blasted desert, rocks oxidized to rust-red hues, any volatile compounds long since boiled away or broken down by ultraviolet exposure, the surface perhaps partially molten in the region directly facing the star where radiation is most concentrated. The night side would be a frozen wasteland, temperatures plunging to near absolute zero in the absence of atmospheric heat transport, perhaps coated with frozen volatiles that have migrated from the day side and condensed in the permanent cold. The terminator region, the boundary between these extremes, might be the least hostile environment, but even there the conditions would be brutal by any standard relevant to life as we understand it, subject to the same radiation bombardment, lacking the atmospheric pressure necessary to stabilize liquid water, and exposed to the continuous particle flux from stellar wind that JWST measurements show bathes the inner system. The implications of these findings extend beyond Proxima b itself to our understanding of red dwarf stars and the planets that orbit them. Red dwarfs are the most numerous stars in the galaxy, and the discovery of rocky planets in their habitable zones had been cause for optimism, a suggestion that habitable worlds might be abundant throughout the Milky Way. But the detailed observations of Proxima Centauri reveal that the habitable zone concept, as traditionally defined, may be misleading when applied to red dwarf systems. Proxima b has none of these protections. The close orbital distance means that the inverse square law works against any planetary atmosphere, intensifying the radiation received during quiet periods and multiplying the destructive power during flares. The stellar wind from Proxima Centauri, composed of charged particles accelerated away from the star's surface, flows past the planet at close range, and without a strong magnetic field to deflect this wind, it can interact directly with the upper atmosphere, stripping away ions and molecules over time, and the question of whether Proxima b possesses a strong magnetic field remains uncertain. Magnetic fields are generated by dynamo processes in a planet's core, requiring a liquid, electrically conductive region undergoing convective motion. Earth's magnetic field is sustained by convection in its molten iron outer core, a process enabled by the heat flowing from the solidification of the inner core and residual heat from the planet's formation. For Proxima b, the conditions necessary to sustain such a dynamo are unclear. Tidal heating from the planet's close orbit might help maintain a molten core, but the planet's relatively low mass and the possibility that tidal locking has reduced internal heat generation raise questions about whether a protective magnetic field could exist at all, or, if it exists, whether it would be strong enough to shield against the intense stellar wind and radiation environment. JWST's spectroscopic observations searched for signs of an atmosphere around Proxima b using transit methods, attempting to detect the absorption signatures that would indicate the presence of atmospheric gases as the planet passed in front of its star from our perspective. The results were negative. No clear atmospheric signatures were detected, no signs of water vapor, carbon dioxide, methane, or any of the other gases that might constitute a substantial atmosphere. The absence of a detection does not prove the absolute absence of an atmosphere. Thin atmospheres or clouds could obscure certain spectral features, and the observations are at the limits of current technology, but the failure to detect any atmospheric signatures when models had suggested that such signatures should be detectable if present was itself informative. It suggested that if Proxima b ever possessed a substantial atmosphere, it either never developed one in the first place, or lost it long ago to the relentless assault of stellar activity. Further observations revealed the mechanism of destruction in even greater detail. During major flare events, JWST instruments detected massive eruptions of plasma from Proxima Centauri's surface, coronal mass ejections on a scale that dwarfed anything produced by our Sun. These plasma clouds, dense regions of magnetized charged particles, sweep outward from the star at high velocities, and when they impact a planet orbiting as close as Proxima b, the effects are catastrophic for any atmosphere. The magnetic fields embedded in the plasma interact with any planetary magnetic field, and in the absence of sufficient protection, the plasma can directly strike the upper atmosphere, compressing it, heating it, and accelerating atmospheric particles to escape velocities. A single major coronal mass ejection impact could strip away a significant fraction of an atmosphere's mass, and with such events occurring potentially dozens or hundreds of times over a planet's lifetime, the cumulative effect would be total atmospheric loss unless geological processes could replenish the atmosphere faster than it is being stripped away. The geology of Proxima b itself became a subject of scrutiny. On Earth, volcanic activity and other geological processes release gases into the atmosphere, a form of planetary outgassing that has sustained and modified Earth's atmosphere over billions of years. Could similar processes operate on Proxima b, continuously replenishing atmospheric gases lost to stellar activity and maintaining a stable atmosphere despite the hostile conditions? The answer depends on the planet's internal heat budget and its tectonic activity. Earth remains geologically active because it retains significant internal heat from its formation and from the radioactive decay of elements in its interior, and because plate tectonics provides a mechanism for heat to escape and materials to cycle between the surface and the interior. Whether Proxima b possesses similar geological vigor depends on factors that are difficult to constrain from observations alone: the planet's composition, the amount of radioactive elements in its interior, the presence or absence of tectonic activity, the rate of tidal heating from interactions with its star. All of these influence the rate at which volcanic gases might be released. In a binary system, the gravitational influence of the companion star can disrupt the protoplanetary disk, truncating it at relatively small distances from each star and inducing turbulence and velocity changes that make it more difficult for planetesimals to collide gently and stick together. Computer simulations of planet formation in binary systems show that planets can form in two configurations: circumbinary orbits, where planets orbit both stars at large distances, far enough that the binary pair acts as a single gravitational source, or circumstellar orbits, where planets orbit one star or the other at close enough distances that the companion star's influence is a perturbation rather than a dominant force. For Alpha Centauri A and B, the orbital separation and eccentricity mean that stable circumbinary orbits would need to be very far from the binary pair, likely beyond 100 astronomical units, cold distant regions where planet formation would be slow and any worlds that did form would be frozen and inhospitable. Circumstellar orbits, planets orbiting just one of the two stars, are possible but only within a relatively narrow range of distances from each star, typically within about 3 astronomical units, beyond which the gravitational perturbations from the companion star become destabilizing over long timescales. Observations of Alpha Centauri A and B have searched for planets in these circumstellar zones, using radial velocity measurements, transit searches, and direct imaging attempts to detect any worlds that might be present. The searches have been extensive and thorough, motivated precisely by the proximity of the system and the possibility that habitable worlds might exist there. And yet, despite decades of observation, no confirmed planets have been found around either Alpha Centauri A or Alpha Centauri B. There have been tentative detections and candidates that were later retracted or remain unconfirmed, but no robust, repeatable detection of a planet orbiting either of the two main stars. This absence is itself informative. If planet formation were easy and efficient in binary systems, if the gravitational perturbations were merely inconveniences that planet formation processes could overcome, we would expect to find planets around these well-studied nearby stars. The failure to detect them despite intensive searches suggests that either planets did not form in this system, or, if they did form, they were subsequently ejected or destroyed by the dynamical evolution of the system. Disk observations provide additional context. Observations of the Alpha Centauri system in infrared and sub-millimeter wavelengths have revealed the presence of debris disks, faint belts of dust, and small bodies orbiting the stars. These debris disks are often interpreted as evidence of ongoing collisional grinding of larger bodies, similar to the asteroid belt and Kuiper belt in our solar system, remnants of the planet formation process. But in the Alpha Centauri system, the properties of the observed debris suggest something different. The dust distribution and the lack of significant gaps or structures that might indicate the presence of planets suggest that the debris represents not the remnants of successful planet formation, but the rubble of failed planet formation, material that never managed to coalesce into large planets because the gravitational perturbations from the binary companion disrupted the accretion process. The debris is evidence of destruction rather than creation, a graveyard of planetesimals that collided too violently to stick together, ground down over time into smaller and smaller fragments. The habitable zones around Alpha Centauri A and B present additional challenges beyond simply forming planets in the first place. The habitable zone around Alpha Centauri A, being similar in mass and luminosity to our Sun, would lie at roughly the same distance as Earth's orbit, around 1 astronomical unit. The habitable zone around Alpha Centauri B, being cooler and dimmer, would lie somewhat closer, perhaps at 0.6 of an astronomical unit. Both of these habitable zones fall within the region where circumstellar orbits could potentially be stable, so the issue is not that habitable zone planets are dynamically forbidden, but rather whether they could survive the long-term perturbations from the companion star. When Alpha Centauri A and B are at their closest approach, separated by only 11 astronomical units, the gravitational influence of the companion becomes significant even for planets orbiting within a few astronomical units of the primary star. These perturbations induce oscillations in orbital eccentricity, forcing planetary orbits to become more elliptical over time than less elliptical, in a cycle that repeats over many orbits. High eccentricity is problematic for habitability because it means the planet's distance from its star varies significantly over the course of its year, leading to extreme seasonal variations in temperature and solar flux that could destabilize climates and make it difficult for life to adapt. Moreover, the gravitational perturbations can interact with other planets if multiple planets exist in the system, leading to orbital resonances and potentially instabilities where planets gravitationally scatter each other, eventually leading to ejections or collisions. The long-term stability of planetary systems in binary star configurations is a subject of detailed numerical simulation, and the results indicate that while stable configurations exist, they are more restrictive and fragile than in single-star systems. A planetary system around Alpha Centauri A or B would need to have formed in a specific architecture, with planets spaced in particular ways to avoid long-term instabilities. The absence of detected planets may indicate that the system never achieved such a stable architecture, or that it did initially, but the architecture broke down over billions of years, resulting in the loss of planets to ejection or collision. There is also the question of whether Proxima Centauri is truly bound to the Alpha Centauri AB binary pair, or whether it is merely passing nearby on an unbound trajectory and will eventually separate from the system. Proxima's orbit around the common center of mass of the Alpha Centauri system, if it is indeed bound, would be highly eccentric and take hundreds of thousands of years to complete, bringing Proxima from its current position of relative proximity to much greater distances before returning. The uncertainty about this orbit and whether Proxima is gravitationally bound arises from the difficulty of measuring Proxima's velocity relative to the binary pair with sufficient precision. If Proxima is bound, then the system is a true triple-star system, and the long-term dynamics become even more complex. If Proxima is unbound, then it is a separate system that happens to be passing nearby, and its eventual departure would reduce the gravitational complexity. But that departure lies far in the future, well beyond any timescale relevant to current habitability discussions. The three-body gravitational dynamics of a triple-star system introduce chaos in the mathematical sense, sensitivity to initial conditions such that long-term predictions become unreliable. Even if Proxima is bound to the Alpha Centauri system, its highly elliptical orbit means that its gravitational influence on the inner circumstellar regions around Alpha Centauri A and B varies dramatically over time. At apastron, when Proxima is far away, its influence is negligible. At periastron, when it approaches more closely, its gravitational pull can perturb orbits, destabilize resonances, and inject eccentricity into planetary orbits that might otherwise be stable. Over billions of years, these periodic perturbations can have cumulative effects, slowly degrading the stability of any planetary system that managed to form. The absence of detected planets around Alpha Centauri A and B may be the result of exactly this kind of long-term dynamical erosion, planets that formed early in the system's history but were gradually perturbed into unstable orbits and lost over time. These findings about Alpha Centauri, taken together, paint a picture that is far removed from the optimistic visions of nearby habitable worlds that dominated discussion just a decade ago. Proxima b, the nearest exoplanet, appears to be an irradiated, airless rock, stripped of any atmosphere it might once have possessed, desiccated of water, and locked in a configuration that concentrates stellar fury on one hemisphere while leaving the other frozen. Alpha Centauri. A and B, despite being more sun-like and ostensibly more promising hosts for habitable worlds, show no evidence of planets at all, suggesting that the binary dynamics either prevented planet formation or led to the destruction of any planets that did form. The Alpha Centauri system, humanity's nearest stellar neighbor, the system we studied first and most intensely, the system we hoped might offer a nearby stepping stone to the stars, appears to be devoid of the kind of habitable, life-bearing worlds that earlier speculation imagined. It is not that the system is boring or scientifically unimportant, but rather that it has taught us a lesson that reshapes our expectations for the galaxy as a whole. The lesson is that habitable worlds are not common simply because rocky planets are common, and that proximity to a star in terms of distance is not the same as suitability for life. Habitability requires a confluence of factors: a stable radiation environment, a planetary magnetic field to shield against stellar wind, a mechanism to sustain an atmosphere over billions of years, a supply of water that is not continuously destroyed by photodissociation, geological activity to recycle materials and replenish atmospheric gases, orbital stability to avoid extreme climate variations, and time. Vast stretches of time during which catastrophic events do not reset the clock on biological evolution. Each of these factors represents a filter, a requirement that a planet must meet, and each filter reduces the number of worlds that pass through. Red dwarf systems fail many of these filters due to stellar activity and radiation. Binary systems fail others due to gravitational disruption and dynamical instabilities. Even single sun-like stars do not guarantee success, as planets must form at the right distance, with the right composition, and avoid the myriad disasters that can befall a world over billions of years, from asteroid impacts to runaway greenhouse effects to the gradual loss of internal heat and geological vitality. The implications for the search for life in the galaxy are profound. For decades, estimates of the number of habitable worlds have been based on the Drake equation and its variants, formulas that attempt to quantify how many civilizations might exist in the galaxy by multiplying together factors representing the rate of star formation, the fraction of stars with planets, the number of planets per star in habitable zones, the fraction of those planets where life actually arises, the fraction where life evolves intelligence, and so on. Early estimates, particularly in the optimistic decades of the late 20th and early 21st centuries, often yielded large numbers, suggesting millions or even billions of habitable worlds and potentially thousands of technological civilizations in the Milky Way alone. These estimates were based on assumptions that rocky planets in habitable zones were common and that a significant fraction would actually be habitable. The Alpha Centauri observations force a downward revision of these estimates, perhaps a dramatic one. If red dwarf systems are largely inhospitable, that removes the most numerous class of stars from consideration. If binary systems have difficulty forming and retaining planets, that removes another large fraction of stellar systems. What remains are single, stable, sun-like stars, and even among those, only the planets that meet all the stringent requirements for long-term habitability and atmospheric retention. Reducing the number of potentially habitable worlds does not eliminate the possibility of life elsewhere in the galaxy, but it does make such life much rarer, more isolated, and less likely to be within reach of our observations or contact attempts. If habitable worlds are separated by hundreds or thousands of light-years, rather than tens of light-years, then the prospects for detecting biosignatures or technosignatures diminish considerably. Radio signals degrade over distance, and the chances that a signal broadcast from a distant civilization would be aimed in our direction, at the right time, with sufficient power to be detected across such distances, become vanishingly small. Interstellar travel, already enormously difficult across the 4 light-years to Alpha Centauri, becomes effectively impossible if the nearest truly habitable world lies 10 or 20 times farther away. The isolation of technological civilizations in such a galaxy would be nearly absolute, each species confined to its own stellar system, aware, perhaps, that others might exist but unable to communicate or visit across the vast distances that separate them. This brings us to the Fermi paradox, the question of why, if the galaxy is billions of years old and habitable planets should be common, we have not detected any signs of extraterrestrial intelligence. No radio signals, no visible engineering projects, no evidence of starfaring civilizations spreading across the galaxy. The paradox assumes that if life and intelligence are common, at least some civilizations should have arisen millions or billions of years before humanity and should have had time to colonize the galaxy, making their presence obvious. The absence of such evidence has been interpreted in many ways, from sociological explanations suggesting civilizations destroy themselves before achieving interstellar travel, to zoo hypotheses proposing that aliens are deliberately avoiding contact, to rare Earth arguments suggesting that life itself is extraordinarily uncommon. The Alpha Centauri findings lend strong support to the rare Earth hypothesis by showing that even systems that appear promising from a distance often fail the detailed requirements for habitability. If our nearest stellar neighbor, the system we expected to be most likely to host habitable worlds simply due to proximity and the favorable characteristics of its stars, turns out to be barren, then the implication is that habitable worlds are genuinely rare. Not because planets do not exist, but because the specific conditions necessary to sustain habitability over billions of years are seldom met. Rarity resolves the Fermi paradox not through mystery or unseen alien motives, but through simple statistics. If habitable worlds are sparse, then so are the origins of life, and technological civilizations become rarer still, the improbable outcomes of improbable processes. In such a galaxy, the silence we observe is not puzzling but expected. There is no one nearby to call us because there is no one nearby at all. Civilizations exist, perhaps, but they are separated by such vast distances that contact is not merely difficult, but effectively impossible, given the constraints of physics and the limited lifespans of both individual beings and technological societies. The universe has not hidden its inhabitants from us through conspiracy or caution. It has simply placed them so far apart that they might as well be alone, islands of thought and awareness separated by oceans of empty space that no conceivable technology can cross within the timescales that matter to biological or even civilizational lifespans. Earth, then, emerges from this analysis not as a typical world, but as an exception, a planet that passed through all the filters and met all the requirements, at least for the span of time during which complex life has existed. Our Sun is a single, stable, middle-aged star that does not produce sterilizing flares. Our planet formed at the right distance to maintain liquid water, with the right mass to retain an atmosphere and sustain geological activity, and with enough radioactive elements in its interior to keep the core molten and generate a protective magnetic field. Our Moon, formed from a giant impact early in Earth's history, stabilizes our axial tilt and prevents the chaotic climate variations that might otherwise result from precession and tilt changes. Our solar system lacks close stellar companions that might have disrupted planetary orbits or bombarded the inner system with comets over time. Jupiter, massive and distant, acts as a gravitational shield, deflecting or capturing many of the asteroids and comets that might otherwise impact Earth more frequently. These are not trivial or inevitable features. Each represents a particular outcome that could have been otherwise, and in most star systems, was otherwise. The more we learn about other planetary systems, the more we recognize how contingent Earth's habitability has been on a specific set of circumstances that do not appear to be common. This recognition does not lead to despair, but to a different kind of awareness, a recalibration of expectation, and a shift in how we think about humanity's place in the cosmos. For much of the modern era, the assumption that life and intelligence must be common was reassuring, a suggestion that we are part of a larger community of minds scattered across the galaxy, that the universe is alive with thought and purpose, that contact or discovery was simply a matter of time and effort. The realization that we may be profoundly alone, that Earth may be one of a relative handful of living worlds in the entire galaxy, separated from any others by distances so vast that contact is impossible, changes the emotional and philosophical landscape. It makes Earth more precious, the sole known refuge of life in a cosmos that is overwhelmingly sterile. It makes human existence more fragile, dependent on the continued stability of this single world with no backup, no nearby haven to escape to if catastrophe strikes. But it also makes knowledge more important, understanding more vital, because if we are rare, then we are the universe's way of knowing itself, the unlikely phenomenon by which matter has organized itself into systems capable of contemplation, observation, and understanding. The study of Alpha Centauri and the detailed observations from the James Webb Space Telescope represent a maturation of our understanding, a movement from hopeful speculation to rigorous measurement, from wishful thinking about nearby habitable worlds to a sober assessment of what the data actually reveal. The universe is not obligated to meet our hopes. It operates according to physical laws that do not care about human desires or narrative satisfaction. Stars behave as their structure dictates. Planets form or fail to form according to the gravitational and collisional dynamics of protoplanetary disks. Atmospheres are retained or stripped away according to the balance between geological outgassing and stellar-driven escape processes. Life arises or does not arise according to chemistry and environmental stability. The universe is indifferent to our presence, neither hostile nor welcoming, simply operating, existing, evolving, according to rules that we are only beginning to fully comprehend. Alpha Centauri was supposed to be special, the nearby system that would prove the galaxy was full of habitable worlds, the destination for humanity's first interstellar probe, the subject of excited speculation and optimistic modeling. Instead, it has become a cautionary tale, a demonstration that proximity does not imply habitability, that the habitable zone concept is a necessary but not sufficient condition for actual habitability, and that the galaxy is a harsher, less accommodating place than earlier generations of scientists and dreamers imagined. Proxima b is not a second Earth waiting to be explored. It is a cautionary example of what happens when a rocky planet orbits too close to an active star, a world stripped and sterilized by forces that operate over billions of years but leave their mark indelibly. Alpha Centauri. A and B are not the stable planet-rich systems that might host biospheres and civilizations. They are a gravitationally complex binary where planet formation appears to have failed or led to long-term instability, leaving behind only debris and dust as evidence of what might have been but was not. The dream of Alpha Centauri as a destination has not died entirely, but it has transformed. It is no longer a dream of finding life or habitable worlds, but a dream of reaching another star system at all, regardless of what we find there, simply to prove that interstellar travel is possible, that humanity can extend its presence beyond the solar system, even if only in the form of tiny robotic probes. Breakthrough. Starshot's vision of sending gram-scale light-sail spacecraft to Alpha Centauri at a fraction of the speed of light remains a technical goal, an engineering challenge that pushes the boundaries of what is possible with laser propulsion and miniaturized instrumentation. If such probes could be built and launched, if they could survive the decades-long journey and transmit data back to Earth, they would return images and measurements from another star system, a historic achievement regardless of whether they find planets or only empty space. But the motivation has shifted from exploration of potentially habitable worlds to simply proving capability, from astrobiology to engineering, from the search for life to the demonstration of reach. The broader implications for humanity's future in space follow similar lines. If the galaxy offers few habitable worlds, if Earth is genuinely rare, then the strategy for expansion cannot rely on finding ready-made Earths elsewhere. Instead, it requires either adapting to environments that are inherently hostile, constructing habitats and terraforming worlds that lack the natural conditions for life, or accepting that humanity's presence beyond Earth will be limited to artificial structures, space stations, and generation ships rather than planetary surfaces. The timescales for such expansion are immense, the costs enormous, the challenges daunting. Without the promise of habitable worlds as destinations, the motivation for interstellar expansion becomes abstract, philosophical rather than practical, driven by the idea of expansion for its own sake or the desire to ensure that human extinction on Earth does not mean the end of human thought and culture entirely. These are valid motivations, but they are not the visceral, immediate motivations that the prospect of discovering alien life or colonizing new Earths would provide. Red dwarfs, the most common stars in the galaxy, remain interesting targets for exoplanet research, but the focus has shifted from habitability to understanding planetary evolution in extreme environments. How do planets lose their atmospheres? What factors determine whether a magnetic field can form and persist? Can any red dwarf systems retain habitable conditions, or are they all systematically hostile? These are important scientific questions, but they are questions about physics and planetary science rather than about the search for life. The discovery that red dwarfs are difficult hosts for habitable worlds has redirected attention toward Sun-like stars, G-type and K-type stars that are less active, and whose habitable zones lie at greater distances from the star where tidal locking and radiation are less problematic. But these stars are less numerous, and the habitable zone planets around them are harder to detect because they orbit farther from their stars and produce weaker signals. The search continues, but it proceeds with tempered expectations. aware that each detection must be followed by detailed characterization to determine whether the planet actually possesses the conditions necessary for life, not just the potential based on distance alone. The philosophical dimension of these discoveries cannot be ignored. For centuries, humanity has grappled with the question of whether we are alone in the universe, whether life and intelligence are common or rare, whether the cosmos is filled with other minds or barren of thought beyond this small world. The Copernican principle, the idea that Earth is not special, that we do not occupy a privileged position in the cosmos, has guided scientific thinking for generations, encouraging the assumption that what happened here should happen elsewhere, that the processes that led to life on Earth should operate on countless other worlds. But the Copernican principle is a philosophical stance, not a physical law, and it can be taken too far. The principle correctly tells us that Earth is not the center of the universe, that our location in space is not geometrically privileged, but it does not necessarily follow that Earth is typical in terms of its habitability or its history. Rarity and the Copernican principle are not incompatible. Earth can be non-central in location while still being unusual in its properties, an outlier in the distribution of planetary characteristics across the galaxy. The emotional response to the possibility of cosmic loneliness varies. Some find it isolating, a diminishment of human significance, a removal of the comforting idea that we are part of a larger community of intelligent beings. Others find it empowering, a recognition that humanity and the life that shares this planet with us represent something genuinely precious and irreplaceable, not merely one instance among many, but perhaps the only such instance within thousands of light years, the sole repository of billions of years of evolutionary history and accumulated knowledge. Both responses are valid. The universe does not care which emotional reaction we have to the facts it presents. It simply is, and our task is to understand it as accurately as possible and then decide what meaning, if any, we attach to that understanding. The silence of the cosmos, the absence of radio signals or visible megastructures, the failure to detect technosignatures or biosignatures despite decades of searching, takes on a different character in light of what Alpha Centauri teaches us. The silence is not a mystery requiring exotic explanations. It is simply the expected outcome of a universe where habitable worlds are rare and technological civilizations rarer still, where the distances between such civilizations are so vast that communication is impractical and contact impossible. The CT programs, searching for deliberate or inadvertent radio transmissions from other civilizations, continue their work, but the expectation of success has dimmed. If the nearest other civilization lies thousands of light years away, if they are as isolated as we are and have no reason to expect anyone is listening, they may not be broadcasting at all. And even if they are, the signal would be so weak and diluted by distance that detecting it would require luck as much as capability, the fortuitous alignment of their broadcast beam with our location, during the brief window of time that our own civilization possesses the technology to detect such signals. The study of exoplanet atmospheres, biosignatures, and habitability continues, but it proceeds with an awareness that positive results may be rare, and that negative results, the absence of biosignatures or the detection of hostile conditions, are themselves scientifically valuable. Each world studied adds to the data set, refining our statistical understanding of how common or rare different planetary types are, how often atmospheres survive around different kinds of stars, what fraction of rocky planets retain water, and, ultimately, how frequently the conditions necessary for life actually occur. This is slow, painstaking work, requiring the most advanced telescopes and years of observation time. But it is work that builds toward a comprehensive picture of the galaxy's planetary demographics, replacing speculation with measurement, hope with data. The James Webb Space Telescope continues its observations, far beyond Alpha Centauri, studying the atmospheres of hot Jupiters and super-Earths, imaging protoplanetary disks to understand how planets form, and probing the early universe to trace the history of galaxy formation and evolution. Each observation adds to the accumulated knowledge, a body of data that future generations will use to ask and answer questions we have not yet thought to pose. The telescope's findings regarding Proxima Centauri will be refined and extended as additional observation time becomes available, and similar studies will be conducted for other nearby red dwarf systems, building a comparative picture of how stellar activity affects planetary atmospheres across a range of stellar types and ages. This work will take decades, but it will eventually provide the empirical foundation for revised estimates of habitable world abundance, moving the discussion from theoretical models to observation-based constraints. The planetary science community has absorbed the lessons from Alpha Centauri and integrated them into ongoing research. Atmospheric escape models now incorporate more realistic stellar radiation environments using actual measurements from JWST and other observatories rather than idealized assumptions. Planet formation simulations include binary star dynamics and explore under what conditions planets can form and survive in gravitationally complex systems. Habitability assessments now consider magnetic field strength, stellar wind properties, and the long-term stability of atmospheric chemistry under irradiation, recognizing that the habitable zone is a starting point for analysis, not a conclusion. The field is maturing, moving from optimistic exploration of possibilities to rigorous evaluation of probabilities, from identifying candidates to critically assessing whether those candidates meet the stringent requirements for actual habitability. For the public and for science communicators, the shift in understanding presents a challenge. The narrative of numerous nearby habitable worlds, of a galaxy teeming with life waiting to be discovered, is compelling and exciting. It has inspired generations of students to pursue careers in astronomy and planetary science, and it has captured public imagination in ways that more pessimistic assessments do not. The reality that Alpha Centauri appears barren, that red dwarfs may be systematically hostile to life, that habitable worlds are likely rare, is less emotionally satisfying, less conducive to the optimistic visions of interstellar exploration and contact that have fueled science fiction and public interest in space. But science is not obligated to provide emotionally satisfying answers. Its obligation is to provide accurate answers, to follow the evidence wherever it leads, and to revise conclusions when new data warrants revision. The story of Alpha Centauri is a story of science working as it should, of hypotheses tested and refined, of expectations adjusted in response to observations, of the gradual accumulation of knowledge replacing speculation with understanding. The technological implications are also significant. If habitable worlds are rare and distant, then the motivation for developing interstellar travel technology shifts from exploration and settlement to purely scientific curiosity or long-term existential risk mitigation. The engineering challenges of interstellar travel are immense, requiring energy expenditures and technological capabilities far beyond anything currently available. Chemical rockets cannot achieve the velocities needed to reach even nearby stars within human lifetimes. Nuclear propulsion systems, whether fission or fusion, can achieve higher velocities but still require decades or centuries to reach other stellar systems. Antimatter propulsion, laser-pushed light sails, generation ships, all of these concepts push the boundaries of theoretical possibility and demand technological advances that may or may not be achievable. Without the promise of habitable worlds as destinations, the investment required to develop such technologies becomes harder to justify on practical grounds, leaving only the abstract appeal of exploration itself or the distant concern about ensuring human survival beyond Earth should catastrophe strike our homeworld. The absence of planets around Alpha Centauri A and B raises questions about planet formation that extend beyond that specific system. Why did planets fail to form or survive there? And what does that tell us about the conditions necessary for successful planet formation? The presence of debris disks indicates that at least some solid material was present in the protoplanetary disk phase, but that material evidently did not coalesce into stable planets. Was the problem related to the binary orbit itself, the gravitational perturbations preventing the gentle collisions necessary for growth? Or did planets form, but then were lost to dynamical instabilities as the system evolved? Distinguishing between these scenarios requires more detailed observations and modeling, simulations that can accurately capture the interplay between gas drag, collisional evolution, and gravitational perturbations in a binary star environment. Understanding the failure modes of planet formation is as important as understanding the success cases, because it constrains the overall frequency of planetary systems and helps us predict where planets are likely and unlikely to be found. The capture hypothesis for Proxima Centauri, the idea that Proxima was not originally part of the Alpha Centauri system but was captured gravitationally as the stars passed near each other in the early history of the galaxy, remains a subject of investigation. If Proxima was captured, then its planets, including Proxima b, formed independently around Proxima before the capture event, and the subsequent dynamics of being part of a triple system would have affected their orbits and long-term stability. If Proxima formed as part of the original Alpha Centauri system, then the planet formation process for all three stars was influenced by the same initial conditions and the same gravitational environment. Determining which scenario is correct requires precise measurements of Proxima's velocity and trajectory, observations that are difficult because Proxima is faint and its motion relative to the Alpha Centauri binary is slow. But the question matters for understanding the system's history and for generalizing the lessons learned to other triple-star systems across the galaxy. The long timescales involved in planetary evolution and habitability are humbling. Earth has been habitable for billions of years, long enough for life to emerge, evolve through innumerable forms, survive multiple mass extinctions, and eventually produce a species capable of studying its own origins and the universe around it. This span of time is so long that it dwarfs human history, civilization, even the entire existence of the genus Homo. And yet, maintaining habitability over such timescales is not guaranteed. It requires continuous geological activity to regulate atmospheric composition, a stable, stellar environment that does not sterilize the surface, an orbit that remains stable and does not drift into regions that are too hot or too cold, protection from catastrophic impacts that might destroy complex life, and countless other factors that must all hold true for billions of years. The probability that any given planet meets all these requirements for such a long period is low, and this low probability multiplies across the many factors that contribute to habitability, yielding an overall probability that may be vanishingly small. Earth has succeeded, but success is not typical. It is the exception, the fortunate outcome that allows us to exist and wonder about our rarity. The concept of biosignatures, chemical indicators in a planet's atmosphere that might suggest the presence of life, has been central to the search for life beyond Earth. Oxygen and methane in the same atmosphere, for example, would be suggestive because these gases react with each other and should not coexist in significant quantities unless some process, such as biology, is continuously replenishing them. But the detection of biosignatures requires that a planet possess an atmosphere in the first place, one that is thick enough and stable enough to be observed spectroscopically from interstellar distances. The findings at Proxima Centauri highlight that many planets we might have expected to have atmospheres do not, and that the presence or absence of an atmosphere is itself a key filter that determines whether a world is even observable from the standpoint of biosignature searches. Even if life exists on a planet, if that planet has lost its atmosphere to stellar activity, we would have no way to detect the life remotely. The biosignature search, therefore, is biased toward planets that not only host life, but also retain atmospheres capable of carrying detectable chemical signatures, a subset of a subset, narrowing further the already small population of potentially observable living worlds. Technosignatures, signs of advanced technology such as radio transmissions, laser pulses, or megastructures like Dyson spheres, represent another approach to detecting extraterrestrial intelligence. These searches do not require that life be common, only that intelligence occasionally arises and that intelligent civilizations develop technology capable of producing detectable signatures. But if habitable worlds are rare, then the origins of life are correspondingly rare, and the evolution of intelligence and technology becomes rarer still, contingent on all the earlier steps plus the additional requirement that life evolves complexity, nervous systems, intelligence, and technological capability. Each of these steps has occurred on Earth, but we do not know how probable or improbable each step was, whether intelligence is a likely outcome of evolution or a rare fluke. If intelligence is rare, then the density of technological civilizations in the galaxy could be extremely low, perhaps only a handful across the entire Milky Way, each isolated by thousands of light-years from any other. In such a galaxy, technosignature searches would be unlikely to succeed unless we happen to be looking in exactly the right direction at exactly the right time, a coincidence that grows less likely as the separation between civilizations increases. The ethical implications of cosmic loneliness are subtle but real. If Earth is the only living world we will ever have access to, if no other biospheres exist within reach, then the preservation of Earth's biosphere becomes not just a local concern but a cosmic one. Extinction of species, destruction of ecosystems, degradation of the environment, all of these take on added weight if Earth's life represents the only known instance of biology in the galaxy. The responsibility to preserve and protect life becomes absolute, because there is no other reservoir of biological diversity to fall back on, no other examples to study or learn from if we destroy the one we have. This perspective does not provide easy answers to the practical challenges of conservation and environmental management, but it does frame those challenges in a larger context, emphasizing that what happens on Earth matters not just to humanity, but to the phenomenon of life itself in this region of the galaxy. The concept of planetary stewardship extends to how humanity manages its own technological development and its impact on Earth. If we are alone, then our survival and flourishing depend entirely on our ability to manage the risks we create for ourselves, from climate change to nuclear weapons to emerging technologies whose consequences we do not fully understand. There is no external rescue, no benevolent alien civilization that will intervene if we fail, no nearby habitable world to evacuate to if Earth becomes uninhabitable. We are on our own, responsible for our own fate, and the universe will not mourn our passing if we fail to navigate the challenges we face. This realization can be motivating, a call to greater responsibility and foresight, or it can be paralyzing, an overwhelming burden of consequence. How we respond to it will shape the next centuries of human history and determine whether the phenomenon of intelligence and civilization on Earth persists into the deep future or flickers out, leaving the galaxy once again silent. The search for life continues, not because we expect quick success, but because the question is fundamental and the tools are improving. Every new telescope, every refined observational technique, every advancement in spectroscopy and data analysis brings us closer to the sensitivity required to detect biosignatures if they exist. The James Webb Space Telescope is only the beginning, the first of a new generation of observatories capable of studying exoplanet atmospheres in detail. Future missions, telescopes larger and more sensitive, instruments designed specifically for exoplanet characterization, will push the boundaries further, studying dozens or hundreds of worlds across a range of stellar types, building the statistical dataset needed to determine how common or rare habitable atmospheres actually are. This work will take decades, perhaps a century, but it will eventually answer the question of whether life beyond Earth exists within detectable range, and if not, what that absence tells us about the universe and our place within it. Alpha Centauri will remain a target of study, not because we expect to find habitable worlds there, but because it is close enough to study in detail, providing a laboratory for understanding stellar activity, planetary dynamics, and the limits of habitability. The system will be observed with every new instrument that comes online, each observation adding incremental precision to our understanding of the stars, the debris disks, the radiation environment, and the faint hope that perhaps some world remains undetected, hidden in the data, awaiting discovery with better techniques or longer observation baselines. The probability of such a discovery diminishes with each passing year and each negative result, but science proceeds through cumulative evidence, not single definitive tests, and the search will continue as long as the possibility, however remote, remains. The cultural impact of the shifting understanding of Alpha Centauri is harder to measure but no less significant. Science fiction has long used Alpha Centauri as a setting, a destination for fictional starships and colonies, a place where humanity encounters alien life or establishes its first interstellar outpost. These stories will continue to be written because fiction is not constrained by current observational data and can explore possibilities that reality does not provide. But the tone and framing may shift, acknowledging the actual findings while still imagining what could be rather than what is. The narrative of Alpha Centauri as a barren system may itself become a theme, exploring the disappointment and recalibration of expectations that comes from learning that the universe is not as we hoped, that the stars we reach for do not offer the welcome we imagined. These stories can be just as compelling as tales of first contact, exploring the human response to isolation and the search for meaning in a cosmos that offers no easy answers. The timescales of cosmic processes dwarf human concerns. Stars live for billions or trillions of years. Galaxies evolve over spans of time so immense that the current structure of the Milky Way is a snapshot in a much longer story of formation, mergers, starbirth, and eventual decline. Against these timescales, human civilization is a brief flicker, a momentary arrangement of matter that will almost certainly not persist in its current form for more than a few thousand or tens of thousands of years. Whether humanity expands to the stars or remains confined to Earth, whether we discover other civilizations or remain alone, in the grand timeline of the cosmos, we are an ephemeral phenomenon, here and gone in an instant. This perspective is not meant to diminish the significance of human life or achievement, but to place it in context, to recognize that our concerns and aspirations, while important to us, are not central to the universe's existence or evolution. The universe was here long before us and will be here long after us, indifferent to our presence or absence, operating according to physical laws that have no awareness of us and no concern for our survival. And yet, within this vast indifference, we exist, and our existence allows the universe to know itself. The matter that composes our bodies and brains is the same matter that was forged in the cores of ancient stars, distributed across space by supernovae, and coalesced into planets and life through the workings of gravity and chemistry. We are not separate from the universe but part of it, a way in which the universe has organized itself to observe, think, and understand. This is not a mystical claim but a straightforward consequence of physics and biology. The universe has produced structures complex enough to model the universe itself, to probe the origins of space and time, to calculate the fates of stars and galaxies, to wonder about their own significance. Whether this is common or rare, whether it happens on countless worlds or only on Earth, it has happened here, and that fact is worth acknowledging, worth preserving, worth considering as we make decisions about how to use the resources and knowledge we have accumulated. The knowledge that Alpha Centauri appears barren does not close the door on exploration or discovery. It redirects focus, channeling attention toward other systems, other questions, other approaches to understanding the cosmos. It teaches us what to look for and what to avoid, which stellar types are most promising and which are likely hostile, what factors matter for habitability and which are peripheral. It forces a more sophisticated understanding of planetary science, moving beyond simple habitability zone calculations to consider the full range of processes that determine whether a world can sustain life over geological time. This sophistication improves the search, making it more targeted and more likely to succeed if habitable worlds exist within range of our instruments. The legacy of the Alpha Centauri observations will be measured not in terms of whether they met initial hopes, but in terms of how they advanced understanding. Science progresses through the accumulation of data and the refinement of models, and negative results are as valuable as positive ones in constraining theories and guiding future research. The discovery that Proxima b lacks an atmosphere is disappointing from the standpoint of astrobiology, but it is informative from the standpoint of planetary science, providing a clear example of atmospheric loss in a high radiation environment and validating models that predict such loss. The absence of detected planets around Alpha Centauri A and B is surprising, given the expectation that binary systems should be able to host planets, but it motivates deeper investigation into planet formation dynamics and long-term orbital stability. Each observation, each measurement, each refined estimate adds to the body of knowledge, and over time that accumulation leads to a more accurate picture of the galaxy and the process that shape it. The silence of the universe is not a silence of absence, but a silence of distance. If other civilizations exist, they are far away, separated from us by gulfs of space that are difficult to comprehend and impossible to cross with any foreseeable technology. They are asking their own questions, studying their own skies, wondering as we wonder whether they are alone. Perhaps some have concluded, as we are beginning to conclude, that habitable worlds are rare and contact is impossible. Perhaps others, more optimistic or more fortunate in their local stellar neighborhood, are searching for signals and finding only noise, the static of natural astrophysical processes with no pattern, no message, no sign of intelligence beyond their own. The galaxy does not facilitate contact. It isolates, separating its stellar systems by light years, separating any living worlds by even greater distances, creating a structure where intelligence, if it arises, does so in isolation, aware of the vastness around it, but unable to reach across that vastness to touch or communicate with anything similar to itself. This isolation is not tragic in the dramatic sense, not a punishment or loss, but simply a condition, a fact about the kind of universe we inhabit. It is a universe of vast scales, where distances are measured in light years and timescales in billions of years, where the speed of light is both the ultimate speed limit and far too slow to make interstellar travel practical, where the energy requirements for even modest journeys exceed the total output of civilizations. It is a universe that allows complexity and life, but does not make them easy, that permits intelligence, but does not guarantee it will be common or enduring, that offers the possibility of understanding, but does not promise that understanding will lead to connection or community beyond the single world where each intelligence arises. The acceptance of this isolation is not resignation, but realism, an adjustment of expectations to match what observation and theory actually indicate rather than what we might prefer. Acceptance allows us to focus on what is achievable, rather than lamenting what is not, to appreciate the rarity and value of what we have, rather than mourning the absence of what we imagined. Earth is rare, perhaps unique within thousands of light years. Life on Earth is precious, the result of billions of years of evolution and the confluence of countless fortunate circumstances. Human intelligence, for all its flaws and limitations, represents a remarkable outcome, the ability to understand and model the universe, to create art and technology, to ask questions about origins and meanings and futures. These are not trivial achievements, not diminished by the realization that they may be uncommon in the galaxy. If anything, rarity enhances value. What is common can be replaced. What is rare cannot. The future of humanity, whether confined to Earth or expanding into space, will be shaped by how we respond to the knowledge that we are likely alone, that the galaxy does not offer nearby havens or alien civilizations to learn from or compete with. We are responsible for our own survival, our own progress, our own mistakes and recoveries. There is no external reference point, no alien wisdom to guide us, no cosmic authority to appeal to. We must navigate the challenges we face using our own knowledge and judgment, making decisions whose consequences will reverberate across generations, shaping the trajectory of our species for centuries or millennia to come. The weight of that responsibility is heavy, but it is the responsibility we have, the condition of existence in a universe that creates intelligence but does not shepherd it. The study of the stars continues, not because we expect to find easy answers, but because the questions matter, and the process of seeking answers is itself valuable. Each observation teaches us something about the nature of stars, planets, and the physical laws that govern them. Each discovery, whether it confirms expectations or overturns them, adds to the accumulated store of human knowledge, the collective understanding that we pass from one generation to the next, building over time into a comprehensive picture of the cosmos. This picture is not complete and will never be complete, but it grows more detailed and accurate with each passing year, each new telescope, each refined theory. The universe reveals itself slowly, grudgingly, demanding patience and precision, rewarding those who observe carefully and think rigorously. Alpha Centauri, the nearest star system, the first destination we imagined reaching, has not offered what we hoped. It has offered something else, a lesson in the difficulty of habitability, the rarity of stable planetary systems, the violence of red dwarf stars, the complexity of binary dynamics. It has taught us that proximity does not guarantee suitability, that distance is only one of many factors that determine whether a world can host life, that the universe is more challenging and less accommodating than early optimism suggested. These lessons are valuable, more valuable in the long run than the brief excitement of confirming pre-existing hopes would have been. They force us to revise our models, sharpen our questions, and approach the search for life with greater sophistication and realistic expectations. The disappointment that comes from learning Alpha Centauri is barren is real, but disappointment is not the end of inquiry. It is a waypoint, a moment of recalibration, an opportunity to refine understanding and redirect effort toward more promising targets. The galaxy contains hundreds of billions of stars. Alpha Centauri is 3 of them. The absence of habitable worlds in this particular system does not preclude their existence elsewhere, only shifts the probabilities and the search parameters. Other stars, more distant but potentially more stable, await study. Other planetary systems, detected but not yet characterized in detail, may prove more hospitable. The search moves forward, informed by the lessons learned, guided by the data accumulated, persistent in the face of negative results because the question of life beyond Earth is too important to abandon, simply because the first few answers were discouraging. The quiet horror of Alpha Centauri is not that it is hostile, but that it is indifferent. The stars shine without purpose, radiating energy into space not to provide light for potential life, but simply because that is what stars do, the inevitable consequence of fusion reactions in their cores. Proxima Centauri's flares are not attacks on Proxima b, but the natural outcome of magnetic field dynamics, oblivious to the planet's presence or the destruction those flares cause. The binary dance of Alpha Centauri A and B is not a barrier deliberately placed to prevent planet formation, but the simple result of gravitational attraction. Two stars orbiting each other because that is how gravity works when two massive objects pass close together. The universe is not cruel, but it is not kind either. It is neutral, operating according to laws that have no awareness of outcomes, no preference for life or death, no concern for whether intelligence arises or is extinguished. In such a universe, the fact that life exists at all, that intelligence has emerged to study the cosmos and understand its own rarity, is remarkable not because the universe intended it, but because it happened anyway, against the odds, without guidance or purpose beyond the workings of chemistry and natural selection. The silence that surrounds us is the silence of a universe that does not speak because it has nothing to say. It is not hiding messages or withholding contact. It is simply empty of other voices, at least within the range we can hear, the distance our signals can reach or our instruments detect. We send radio signals into space, broadcasting our presence, and they travel outward at the speed of light, diminishing in strength with distance, eventually becoming indistinguishable from background noise. If another civilization exists thousands of light years away, our signals will not reach them for thousands of years, and their reply, if they choose to send one, will take thousands of years to return. The timescales make conversation impossible, contact impractical, awareness of each other's existence a historical curiosity rather than a basis for interaction. We are alone, not because the universe is empty, but because the universe is too large, the distances too vast, the timescales too long for connection to form across the gaps that separate one living world from another. This is the reality that Alpha Centauri has helped us understand, not through a single dramatic revelation, but through the accumulation of observations that collectively paint a picture of a nearby stellar system that does not meet the requirements for habitability. The James Webb Space Telescope provided the detailed measurements that confirmed what earlier, less precise observations had suggested, that Proxima b is irradiated and likely airless, that Alpha Centauri A and B lack detected planets, that the system as a whole does not offer the nearby habitable worlds that earlier speculation imagined. These findings are not the end of the story, but a chapter in the longer narrative of humanity's exploration of the cosmos, our attempt to understand where we came from, whether we are alone, and what our future among the stars might hold. The universe stretches beyond Alpha Centauri, billions of light years in every direction. Filled with galaxies and stars and planets and phenomena we are only beginning to catalog and understand. The fact that our nearest neighbor is barren does not mean the entire universe is barren, only that the conditions necessary for life are more restrictive and less common than we hoped. Life may exist elsewhere, on worlds we have not yet discovered, around stars we have not yet studied, in regions of the galaxy far from our own. But if it exists, it is distant, beyond our reach, beyond our ability to detect with current technology, perhaps beyond our ability to ever confirm or contact. We are left with the life we know, the life that shares Earth with us, the only confirmed instance of biology in the cosmos. That is enough. It has to be enough, because it is what we have, the only data point, the sole example from which we attempt to extrapolate the nature of life in the universe. The contemplation of cosmic isolation does not lead to nihilism if we do not let it. Meaning is not something the universe provides. It is something we construct, individually and collectively, through our choices and actions and the stories we tell about why those choices and actions matter. The universe may be indifferent, but we are not. We care about what happens, about the survival of our species and the preservation of the biosphere, about knowledge and beauty and the alleviation of suffering. These concerns are human concerns, not cosmic imperatives, but they are real and significant within the context of human existence. The fact that they do not matter to the universe at large does not diminish their importance to us. We create meaning in a meaningless universe, and that creation is not futile but necessary, the foundation upon which civilization and culture and cooperation are built. The stars will continue to shine, Alpha Centauri among them, indifferent to our gaze, unaffected by our conclusions about its planets or lack thereof. Proxima Centauri will continue to flare, stripping away any remnants of atmosphere from Proxima b, completing the work of destruction that has been ongoing for billions of years. Alpha Centauri A and B will continue their orbital dance, slowly circling each other over decades and centuries, their mutual gravity shaping the space around them but producing no worlds, only debris and dust. The system will persist, unchanged by our observations, unaware of our disappointment, existing as it has existed for billions of years and will exist for billions more, a collection of stars and orbits and radiation environments that happen to be nearby in galactic terms but offer nothing to the dreams of exploration and contact that humanity has nurtured for generations. And we will continue, here on Earth, observing and studying and wondering, building telescopes and models and theories, searching for patterns and explanations, asking questions about the nature of reality and our place within it. The search for life beyond Earth will continue because the question is fundamental, even if the answer, when we finally obtain it with confidence, is that life is rare and we are alone. The knowledge is worth having, the uncertainty worth resolving, even if the resolution is disappointing. We are a species that seeks understanding, that cannot comfortably live with unanswered questions, that builds instruments and dedicates careers and spends resources to probe the unknown. This drive has carried us from ignorance to knowledge, from superstition to science, from confinement on Earth to tentative steps into space. It will carry us further, not to nearby habitable worlds, because they do not appear to exist, but to deeper understanding, more refined knowledge, clearer pictures of what the universe contains and how it operates. The universe is vast and old and mostly empty, dotted with islands of matter that occasionally organize into stars and planets and, very rarely, into life and intelligence. We are one such island, isolated by distance from any others that might exist, shaped by processes that we are only beginning to fully understand, the product of billions of years of cosmic and biological evolution that led, improbably, to this moment of awareness and questioning. The fact that we exist to ask these questions, to build telescopes and study distant stars, to wonder whether we are alone, is itself remarkable, a statistical fluctuation in a universe that is overwhelmingly sterile and empty. We are not central, not privileged, not cosmically significant, but we are here and we are aware, and that awareness allows us to see and understand, to create knowledge from observation, to find patterns in chaos, to impose temporary local order on a universe that tends toward entropy. Alpha Centauri will remain visible in southern skies, a bright point of light that looks from Earth's surface no different than it did before we learned anything about it. The knowledge that it hosts no habitable worlds, that its system is barren and hostile, exists only in our minds and our databases, invisible to casual observation, requiring instruments and analysis to reveal. Future generations will look at that same point of light and know what we have learned, and they will direct their attention elsewhere, toward other stars that might prove more promising, toward questions that remain unanswered, toward the ongoing project of understanding the cosmos and our place within it. The dream of Alpha Centauri as a destination has faded, but the dream of understanding, of knowledge, of pushing back the boundaries of ignorance, that dream persists, redirected but not diminished, disappointed but not defeated. The silence is complete. The universe offers no reply to our questions except the data we extract through observation, no guidance except the patterns we discern through analysis, no comfort except the satisfaction of understanding. We are alone with that understanding, isolated by distance from any others who might share it, responsible for preserving and extending it, passing it forward to those who come after us. This is the condition of intelligent life in a vast and ancient universe, a condition we are beginning to fully grasp through studies of nearby stars like Alpha Centauri, through observations that reveal not the galaxy we hoped for, but the galaxy that actually exists, indifferent and immense, beautiful and harsh, knowable but uncaring. We observe, we measure, we understand, and we continue, because that is what we do. The nature of intelligence in a cosmos that did not design us but produced us anyway. Matter become aware, the universe knowing itself through us. Briefly, in this small corner of space, before the light fades and the silence returns and all evidence of our existence dissolves into the entropy that awaits all structures, all complexity, all thought, given enough time.